Okay, so I guess there are no questions, and we'll start today's lecture. As I said, I'd like to start today's lecture by reviewing briefly the original formulation of this monogamy paradox by Mathur and by AMPS, which was in terms of the strong sub-additivity of the von Neumann entropy. So let me just start by reminding you of this Penrose diagram that we had yesterday. It'll keep appearing today as well, so I'm just going to copy it. And let me just remind you roughly what the idea was. The idea was that we consider a black hole that is formed from collapse. So this badly drawn dust that you see here is a thing that collapsed to form the black hole. And then this is the trajectory of the, you can think of a star, and this is the surface of the star, the thing I'm tracing. And then after it has collapsed, you form a black hole, and the black hole evaporates and in the end vanishes. But sometime in the late stages of black hole evaporation, we draw a Cauchy slice through the geometry, which is this slice. And on the Cauchy slice, we mark out some regions. In particular, we marked out this region, which was A, the region outside, just outside. And there was B, which was inside or just inside. And then there was C, which was, which was a radiation which contained the early Hawking radiation. So that's the region far away, okay? Far away from the black hole. Okay, so we had these three regions, and yesterday we tried to construct a paradox by writing down some operators in A and B, and then using some arguments from quantum information to suggest there should be some other operators in C, so that when you take all of these operators together, you end up violating the monogamy of CHSH correlators. But it's useful and it's nice in some ways to also think in terms of the von Neumann entropy of these regions. And so let me now try and explain how considering the von Neumann entropy of these regions leads again to the same kind of paradox. Before I do that, I just wanted to say something which I said yesterday, but maybe I should reiterate. The idea is that we want to consider quantities like SA, SB, SC, maybe SAB, SAC, and so on. Okay, so we want to consider quantities of this kind. So SA is, of course, the entropy of A, and similarly for SB and SC, this is the entropy of A union B. Okay, so if you take the region A and B together, then that itself is some region in the Cauchy slice, and we want to ask questions about the entropy of A union B. And similarly, this is the entropy of A union C. We might also want to ask about the entropy of, say, B union C. And of course, the assumption that underlies all of these arguments is that this von Neumann entropy is somehow a well-defined object. So, as we said yesterday, the assumption that underlies the whole argument is that there is a factorization of the Hilbert space, and the big Hilbert space, which is the H that we have here, contains these three factors, which are HA, HB, and HC. And when that happens, you can then consider these quantities, which are SA, SB, SC, SAB, and SAC. Okay, okay, good. Now, the reason, I didn't originally state this paradox in terms of the von Neumann entropy is that in a quantum field theory, this is something that one could do. But in a theory of gravity, even if one assumes, so we've already made the assumption that there is some effective factorization, but even if one assumes this factorization, we still don't have a very good sense of how to define these quantities. And the reason is that all of these are UV divergent. Okay? And in a QFT, we know how to regulate those UV divergences. We know how to regulate it in that, you put some cutoff, and once you put a UV cutoff, you know what the dependence on the cutoff should be, and so you just subtract that off, and you're left with the finite part. But in a theory of gravity, we don't know how to define this quantity. Even if you assume factorization, there are just UV issues with how to define this quantity. And so somehow, in what I'm going to say, we are going to have to assume that our naive intuition about these entropies continues to hold. So, what we will largely need in framing the paradox in terms of the von Neumann entropy is a notion of some inequalities. We'll have to say that when two systems are entangled, the entropy is lower than what it is when the systems are disentangled. And we'll have to assume that this intuition continues to hold even when gravity is present, and even though we don't really know how to define these quantities very precisely. Okay? So in addition to factorization, we are also going to have to make this additional assumption about the von Neumann entropies. So all that being said, let me just start and give you the argument, which is actually quite simple and nice to state. So the first part, as usual, remember that the way the monogamy paradox goes is that we look at this diagram and we say that A and B have to be entangled because that's how the black hole works. And when you emit Hawking radiation, there's some entanglement between pairs of particles on opposite sides of the horizon. And then we say, well, but from general arguments, it must be the case that A and C must be entangled. And therefore, we run into a paradox with the monogamy of entanglement. So we are now going to make precisely the same argument using the von Neumann entropy. Okay. So the first consider A union B. Let me put this diagram so you know every time what we're talking about. So A union B is a region on opposite sides of the horizon, the region just outside the horizon, union the region just inside the horizon. So this is the near horizon region taken on both sides of the black hole horizon. So now, we've been saying that the Hawking radiation is entangled with some modes that are behind the horizon. And remember, there are various ways we derive this. We derive this by looking at the short distance behavior of correlation functions. But even in Hawking's original derivation, the fact that A and B both came from the neighborhood of a point on scry minus told you that degrees of freedom in A and B had to be entangled together. And the mathematical way to state this in terms of the von Neumann entropy is that we say that SAB is smaller than SA and SAB is smaller than SB. Okay? And the reason for this is that notice if A and B are entangled, then AB together are less mixed than A by itself. Okay? And AB together are less mixed than B by itself. Right? This is pretty simple to understand. If you take if you have some EPR pairs, let's say you have a system of 5 qubits and 5 qubits, and some of the 5 qubits in the left hand are entangled with some of the 5 qubits in the right hand, then it will necessarily be the case that when I take the system of 10 qubits that has some entropy which is smaller than the entropy of just one and the entropy of the other. And that's the argument, the first argument that we are going to need to make. I see there's a question in the chat. Can I please give some references for why the usual regularization of entanglement entropy does not work? So the question is, are there any references for how this is done? I'm afraid actually I don't know of any very good references for where this has been done. One of the things one could try and do, well, there are many complications in trying to define the entanglement entropy in the theory of gravity. The complication even before we arrive at the issue of regulating the UV divergences is that we don't know how to define a good notion of the set of operators that belong to a region, and with one exception, and that exception is when the region we are talking about is the entanglement wedge of some region on the boundary in ADS-CFT. In that setup, we probably do have a good understanding of what entanglement entropy means also in a theory of gravity. And in that setup, there has been some exploration of how these UV divergences and so on are regulated. That's, of course, the usual discussion of Ryutakenagi formulas. But when we talk about regions of this kind, notice that none of these regions, A, B, or C, are not entanglement wedges of anything. Even if you think of a black hole, a small black hole that's evaporating in ADS and not in flat space, you will see that the geometry of the situation, which is one where C surrounds A and B. So A and B are, these are like nested regions. So B is inside A, which is inside B. And entanglement wedges don't have this kind of a structure. You don't have an entanglement wedge which completely surrounds another entanglement wedge. There isn't actually any good literature. I don't know of any good place where the question of how the UV divergences can be regulated has been discussed. If somebody else knows, please type it in the chat, but I actually don't know the answer. I don't know of any good references where this is discussed, but it clearly is an issue. If you were to try and define the entanglement entropy of regions that are not entanglement wedges in gravity in some way, and you found some way to sensibly define that quantity, you would have to deal with these divergences. I don't know of a good place where this is discussed. Okay. So sometimes the statement that SAB is smaller than SA and SAB is smaller than SP is stated in a slightly different way. It's the fact that, we say that A and B, or the degrees of freedom in A and the degrees of freedom in B, are almost maximally entangled with each other. If that is the case, we would actually like to say that SAB is almost 0. Okay? And we would like to say that SA is almost the same as SB. Okay? So this is the statement that AB are maximally entangled. And indeed, if one thinks of the simple harmonic degrees of freedom, it is kind of the case, as even we argued yesterday, it looks like the degrees of freedom in A and the degrees of freedom in B kind of factorized from the rest of the Hilbert space. So if one takes that very seriously, then one would say that, SAB is close to 0 and SA is approximately the same as SP. We actually, to set up the paradox, we don't need the stronger thing that's written below. We just need the weaker assertion, which is on top, which is that SAB is smaller than SA and not that SAB is close to 0. So to set up the paradox, it's sufficient to argue for this. Okay, great. So now this is about A and B. So let's go back to this. The next thing to consider is the entropy of SC. Okay? So what about the entropy SC? So there's this region far away, and what do we expect for the entropy of this region far away? So under the assumption of factorization, and this is important, and it is something we'll discuss later as well. Under the assumption of factorization, by factorization I mean factorization of the Hilbert space, we expect that this object SC will obey a page curve. And the reason we expect it will obey a page curve is because we say the black hole is evaporating the same way as a non-gravitational, if you just look at a black hole from outside, it just looks like some object with some degrees of freedom, and then it evaporates. And once it evaporates, you collect the Hawking radiation. And that process, in that process, if you're far away from the black hole, as we said yesterday, you assume that, gravitational effects are not important. And therefore, you expect that the radiation from the black hole will carry information at the same rate as the radiation from, say, a piece of coal or some other non-gravitational object. And if you assume this, then you expect that the entropy SC obeys a page curve. Okay? So let me just remind you what the page curve was. Okay. So this is time. At the beginning, there is no radiation in SC. So if you've somehow found a way to subtract off the entropy of the vacuum, at the beginning, this entropy is just 0. And then it rises steadily according to, because Hawking tells us that you get thermal radiation. If you get thermal radiation, that contributes a thermal amount to the entropy. And so the entropy rises steadily. And then it falls after some time. And the reason it falls is one of the results we proved in quantum information, where we said that, if you take a system and you divide it into two parts and you move the partition from one side to the other side, this is how you expect the entropy of one side of the partition to look like. And if we think of the process of black hole evaporation as being this process where, you have some information or some matter or some qubits which are sitting inside the black hole, and then those qubits are, somehow emerging gradually from the black hole, then you do expect that the entropy of these qubits when you're far away will, obey this kind of a page curve. Okay, so this is the expectation for the entropy of SC. As I said, it requires an assumption of factorization, which we'll come back to later, and it, requires an assumption that we've somehow managed to subtract off the entropy of the vacuum and regulate all of these other issues. Okay, good. So are there any questions at this point about this entropy of SC?
I have one. The first time we studied the page curve, the x-axis was the portion of microstates in the smaller system, right?
Correct.
How can we say that this is linear in time? And which?
Sorry. Thank you for the question. Actually, it's not linear in time. So I've rescaled time in a way. The fact that I've drawn it as a straight line is actually not accurate. You would draw it in a different way if you really had time. This is actually a schematic figure. So thank you for that question. Page has actually done some computations in which he has estimated how this entropy really was to behave. And you would have to be a little bit more careful in estimating this entropy. There are various effects that would come out. that have to do with the time dependence. So this is schematic. All I want to say is that it rises on one part and then it falls. Okay? Not that it's a straight line. Thank you for that clarification.
Thank you.
Yeah. Okay, great. So now let me say one more thing. You see, let's look at the part of the page curve which is falling. So that's this part of the page curve. Okay, so let's look at an old black hole which is past this time in the middle, and this time is what we will call the page time. So let's say we look at an old black hole that's past its page time. So the entropy of this radiation is actually decreasing. If this is the case, then notice that at time t plus delta t, what is the process that happens in terms of the figure that we had? You see, at time t plus delta t, what is going to happen is that some additional degrees of freedom are going to move from A to C, if you see the arrows I'm drawing here, right? So if you think of what's happening physically, what's happening is that some degrees of freedom are moving from A and they're moving into C. So at time t plus delta t, let's say you wait for enough time so that all the radiation in A goes into C. Then you see that at time, if that's the time delta t, then you see that at time t plus delta t, what is now C is what was earlier A and what was earlier C. Okay. So the fact that SC at t plus delta t is smaller than SC at t for t larger than t page, this implies that SAC is smaller than SC. Okay, and the reason is what I just said. It's the fact that t at t plus delta t, the new C is what was the earlier A and the earlier C. So the fact that the new C has a lower entropy than the old C tells you that AC has a lower entropy than C. This is another way of saying that degrees in freedom in A have to be entangled with degrees of freedom in C. So this is, again invoking this result that we had about entanglement in a generic state in a large system. It tells you that if you take a large system and you divide it into two parts, in this case, one of the parts is A and the larger part is C. Then in general, the partners of A are all sitting inside C, and therefore the entropy of AC is smaller than the entropy of C by itself. Okay? The way we have stated the argument here is slightly different. We have said, we have a page curve, and then we go to the later part of the page curve, and then, we have this, the time variation of the page curve, and then we said, physically, this means that, radiation from A is going into C, and that's why SAC is smaller than SC. But really, it's invoking the same argument. If you go back to our derivation of the page curve, this is where the derivation came from. And it's really saying the same thing. It's the fact if you take a big system, then the partners of the operators in the smaller half are sitting in the larger half. And that's true for a generic state. Okay. So now we have these two results. We have this result. Let me just remind you, we have the result. One of them is that SAB is smaller than SA. SAB is smaller than SE.
Sorry, I have a question.
Yeah.
So if the degrees of freedom are moving from the region A to region C, can we say that these two Hilbert spaces factorize?
Sorry, can you speak up a little bit? I couldn't hear.
Yeah, sorry, can you hear me now?
Yeah.
So I'm saying that if you're saying that the degrees of freedom move from the region A to region C, can you still say that the Hilbert space of A and C factorizes?
Yes. The Hilbert space of A and C factorizes, but you could still have energy that flows from A to C, right? So you see, it could still be, the way to think about this is think of a quantum field theory. In a quantum field theory, you have some photons that are here, and there's some photons in the other room. So now in a quantum field theory, the Hilbert space of this room factorizes from the Hilbert space of the other room. But we want to somehow look at the degrees of freedom that are on top of the vacuum. And so the idea is you have some photons here and some photons there, and the photons from here can move physically from this room to that room, and they might be entangled with the photons in that room. But it's still true that the Hilbert space factorizes. So the Hilbert space factorizes, but that doesn't preclude the fact that information or energy can move from one side to the other side. So as I said, the intuition here is that you're thinking of some kind of qubit or some kind of gas of photons. And when I say that the information from A moves to C, it means that the photons from A or the gravitons or whatever is emitted moves from A into C. But there's still a good sense in which the degrees of freedom in A are distinct from the degrees of freedom in C. But you could still have the fact that energy or information could move from one side to the other. They could be coupled to factors.
Right, and just another question. So this, the fact that these degrees of freedom are moving from region A to C is also true before the page time, right?
It is also true before the page time, but notice this is not true. Yeah, it's also true before the page time, but this is the equation that is not true before the page time.
That's
so before
true.
the page time, SAC is larger than SC. Okay, so this inequality is only true after the page time. Before the page time, the inequality is reversed. SAC is larger than SC. After the page time, this is the inequality. Okay, so that's the important part of the page time.
Sorry, can you just repeat how from this first line you get the second line?
You see, the at t plus c at t plus delta t is, so I'll write down something which is not an equation, but is AC at t. Okay, that this is not an equation, but it's roughly the statement that the information in C, or the photons in C at time t plus delta t, are the photons in A at time t and the photons in C at time t. So what is in C remains in C, but what is in A moves into C. Okay, that's why. So that's why SC at t plus delta t is the same as SAC at an earlier time. So that's the intuition.
Okay, thank you.
Okay, thank you. Great. So now we have these two results, but now there's the von Neumann entropy is an object which has been studied, and
Suvrat, I think Tunir has a question.
Yeah. Am I audible?
You're not very audible, but yeah, go on. Yeah.
Yeah. Is it better now?
Yeah.
Oh, okay. Yeah. So I had a problem with the previous diagram. So in the previous class, you showed that the page curve turns around when the fraction of the bipartition changes from minor to major, right? But I'm not sure how you're saying that the fraction of degrees of freedom that are in C is changing over time.
Because the radiation is causing photons to move from A, B into C. If you think of so that's why there are more photons, so there is more gas that's now in C than was there earlier. So if you think of the entire black hole as being made up of a chain of qubits that's sitting on top of the vacuum, some of the qubits broke off from the black hole and moved into the region C, and therefore now there are more qubits in C than there were earlier in C.
I see. But the Hilbert space is still not changing, right? It's only the state, the quantum states that's changing.
Yeah, it's the quantum state that's changing. Correct.
Right.
It's the quantum state that's changing. Yeah.
Right. But in the previous class, the important fraction was S divided by S plus S prime, and that depended on the dimensionality of the Hilbert space, right?
Yeah. So in this situation, you're right. In this situation, what's happening is that you have an infinite dimensional Hilbert space on both sides. Because you have a quantum field theory and you have an infinite dimensional Hilbert space. But the way you should think about it is that, think of a quantum field theory and think once again of this room and the other room. And in this room and the other room, you have a gas of photons, and the photons go from this room to the other room. Okay, so when this happens, the dimensionality of the Hilbert space really of neither of this room nor of the other room changes, because that's just being described as a Fock space, and that's actually infinite dimensional. But there's some sense effectively in which radiation or the photons move from one to the other. And that's what's happening here. And if there are 10 photons together, once the division of photons is 6 and 4, then more of the information is in the room which has 6 photons, and less of the information is in the room that has 4 photons.
Okay. Okay. So S and S prime are still changing, but the dimensionalities are not.
Correct.
Okay. Thanks.
Okay. Great.
Can I ask a question?
Yeah.
Why do you need a different argument for SAC smaller than SC than you had for SAB smaller than SA, say?
There are different things that are happening. SAB is smaller than SA is happening because in the process of Hawking radiation, modes across the horizon are entangled with each other. SAC is smaller than SC is true only after the page time. It's happening because we're assuming the page curve. So A and C together, A and C could be very large, and maybe it could have a lot of Hawking radiation. And it would not necessarily be the case that, or maybe A could have some radiation. It would not be the case that SAC was smaller than SC in general. In fact, it's not true before the page time. So there are different origins to these two inequalities. Okay. So just to go back to the argument, there is, the von Neumann entropy satisfies some inequalities, one of the inequalities that the von Neumann entropy satisfies is the inequality that SAB plus SAC is greater than equal to SB plus SC. Okay? This is called the strong subadditivity inequality. And this strong subadditivity inequality you can think of as representing a version of the monogamy of entanglement. Okay? Why does it represent a version of the monogamy of entanglement? The reason is quite simple. The reason is that let's say A and B together were entangled. Okay, so let's say, once again, think in terms of qubits. Let's say A and B together were entangled. Then it would be the case that SAB would be very small. Right? So if AB are entangled, then SAB would be small. Okay? Then SAB is small. But you see, what this inequality tells us is that it cannot also be the case at the same time that SAC is too small. Okay? So then SAC cannot be too small. I mean, I'm writing words here, but the precise equation is on top. So SAC cannot be too small, and too small is defined by SB plus SC, and therefore A and C cannot be entangled. Okay? So this is one way you would interpret the strong subadditivity of von Neumann entropy as a notion of the monogamy of entanglement. It's different from what we said previously about the monogamy of CHSH correlators, but it's still something that can be interpreted in terms of the monogamy of entanglement. It's another statement of the same physical fact that if A is entangled with B, A cannot also be entangled with C. Okay? But notice that here we are obviously in trouble. Okay? We are in trouble because we said SAB is smaller than SB and SAC is smaller than SC after the page time. And clearly, these two statements are in contradiction with this. Okay? So there's a paradox between what we just derived and the strong subadditivity of von Neumann entropy. Okay? And this is the same paradox that has to do with the monogamy of entanglement that we derived earlier. So I'll now go on to say a few more things about this paradox. Let me just say that I think it's worth reading the original place where this paradox was formulated. It was formulated in archive by Mathur, as I said, and you'll find the strong subadditivity of von Neumann entropy there. If you look at the original text where this paradox was formulated, it was not actually formulated by talking about regions of space and so on. It was formulated by just thinking about bit models. And in fact, this intuition of bit models is indeed something that runs throughout these kinds of discussions. We've just slightly generalized that by talking in terms of regions of space and so on. But really, essentially, this is the same paradox. Okay. So now what I want to do for the remaining hour in the lecture is discuss three possibilities, actually largely discuss two possibilities and mention a third for how this paradox can be resolved. Okay? So in particular, we want to discuss three proposals, and the last one we'll spend more time on later and maybe not so much time on today. So let me just make a table and then I'll write down what the proposals are and I'll try and explain what the evidence for each proposal is and what the criticism of each proposal is. So as I said, this proposal was initially invented to make a case for fuzzballs. And so the first thing I want to try and describe is how the fuzzball proposal would resolve this monogamy paradox. Okay? So the fuzzball proposal resolves the monogamy paradox whenever you see, the main point of inventing this proposal from the point of view of fuzzballs. So I'll keep coming back to the slide, but let's just go on and discuss fuzzballs and we'll come back to the slide. So fuzzballs are the statement that black holes evaporate like ordinary objects. So black holes evaporate the same way a lump of coal does. Okay? So a lump of coal evaporates, or you have a chain of qubits that evaporates, and the fuzzball proposal is a statement that black holes just evaporate in the same way. Okay? Now, what is different about the way ordinary objects evaporate and the way black holes evaporate? If I burn the computer in front of me, what is different about the way the computer is burning and the way something else is burning? And it's actually pretty obvious, if you draw a diagram. So here's our coal, right? And maybe the coal has emitted some thermal radiation, right? And here's some thermal photons or gravitons or whatever, some radiation which has been emitted. Okay? And this radiation still obeys a page curve. It's still reducing energy from the coal, and all of that is happening. But the important point about the way ordinary objects evaporate is that ordinary objects have no interior. And when I say, or actually have no interior partners, I mean ordinary objects have an interior, but they have no interior partners for emitted radiation. Okay. So, when you emit radiation from coal, there is nothing that tells you that every qubit that is emitted from a coal is maximally entangled with a qubit that remains behind in the coal. It might be, that you had an EPR pair and the EPR pair broke and the qubit that was emitted was entangled with the qubit that got left behind. But there is no rule that tells you that this is necessarily the case for a piece of coal. Okay. So the important part is that ordinary objects have no interior partner for emitted radiation. And in the context of a black hole, it is the statement that the black hole has no interior. Okay? It has no interior. In fact, it doesn't even have a horizon, as I'll say in a minute. But the black hole has no interior. And this would be the statement of the Fuzzball proposal. I'll refine the statement in a minute. But at zeroth order, the statement is that there is no horizon and there is no interior. And mathematically, which of the equations does it drop? It drops the equation that SAB is smaller than SB and SAB is smaller than SA. Okay? So it drops this equation. And the reason it drops this equation is because, B doesn't even exist. There is no partner. Just to remind you once again, what A and B meant. The Fuzzball proposal says, this is not the right Penrose diagram to think about. There is no region B which is maximally entangled with A at all times. It is still true that A obeys, the entropy of C obeys a page curve. And so, it might be the case that when your black hole was small and in the early stages of evaporation, the photons that are emitted are entangled with something that remains behind. But at late times, it's no longer true that the photon that's emitted is entangled with something that remains behind. The photon then is only entangled with C. It is not entangled with B. Okay? So at late times, the statement is at late times, A is only entangled with C. So that's the resolution to the monogamy paradox, right? We say A is only entangled with C, A is not entangled with B, and therefore we are done, right? We got rid of the monogamy paradox. But of course, when we get rid of this monogamy paradox, we have this trouble that, we are saying that, the black hole or the black hole solution that we thought existed, and, we had this Tolman, Oppenheimer, Volkoff solution, or and this of collapsing dust, or maybe some Vaidya solution. And now we are saying, that's actually not true, and the black hole doesn't really have an interior, and something else happens before the horizon appears and stops the interior from existing. So let me just try and refine a little bit more what the clever idea in the Fuzzball proposal was, and let me also try and explain in what sense those who advocate the Fuzzball proposal say that there should be an effective interior. So the first point is that
Suvrat, there's a raised hand. Do you want to take it now, or?
Yeah, maybe I'll take it in a couple of minutes. Let me just say
Okay,
a
cool,
few
cool,
things. Okay. Yeah. Okay. So the Fuzzball proposal says the following. It says, there is something that these ideas that black holes might have structured the horizon or something might stop them from collapsing are in a sense old ideas, right? They're old ideas that people thought about even earlier, and the whole point of talking about the Chandrasekhar limit of a star, or talking about was to say that once you're beyond a certain point, there is nothing that can stop the star from collapsing. And what is more, after the star has collapsed, it's not possible to put hair at the horizon and somehow create structure at the horizon and store all the information at the horizon. There are these theorems that suggest that the solution tends to something universal at late times. So the clever idea of the Fuzzball proposal is to use an extra dimension and use some topological obstruction to the horizon forming. So I'm going to try and draw a cartoon of what the proposal is. So let's say this is the radial direction. So this is the radial direction. And here is where R equal to RH was going to happen. So the idea of writing down solutions or writing down fuzzball solutions is that we recognize the fact that in string theory, one of the things that we have learned is that in order to make the theory consistent, we require extra dimensions. And so we introduce an extra dimension, and the extra dimension is such that it pinches off before. So this is the extra dimension. And the extra dimension pinches off before R equal to RH is achieved. Okay? And because the extra dimension pinches off, in some sense, space ends, space-time ends before the horizon is achieved, before you reach the horizon. And because that happens, that is how collapse is stabilized. So collapse is not stabilized by saying that, we have to have some exotic equation of state which exerts huge amounts of pressure and somehow stops collapse from happening. If one was to try and do that, one would run into many difficulties. If you take, like, say, Sagittarius A star, and you were to try and ask, what is the, we've seen some orbits of stars that are going around Sagittarius A star. So we know that, Sagittarius A star, whatever it is a compact object, which is quite small. And you could then try and ask, what is the equation of state that you would need for some lump of dust to be stable, so that you can have these stars which are orbiting close, and all the dust, all the matter is confined in a small region, and that often ends up being something that's just incredible, and not something that you can find an equation of state of matter to support this kind of mass in such a small region. And so the clever idea of the fuzzball is to come up with this topological obstruction to collapse by using some extra dimension which pinches off. And then in different ways, this extra dimension could pinch off in different ways. This would then lead to different kinds of microstates for the black hole. So this is, in some sense, the clever idea of the fuzzball. And because the black hole pinches off and the black hole never forms, there is no notion of an interior, and we don't have a problem with the monogamy of entanglement. So there was a question. I can take a question now, actually.
Hi, Suvrat, it's me. I was just a bit confused about your argument on how the fuzzball proposer evades the monogamy paradox.
Yes.
Because, how did you call your mode outside the horizon? Was it B?
I'm sorry, can you say once? How did
the mode just outside the horizon? Oh, it's A.
This is A.
If I have something that strongly resembles, the horizon played an important role here, but not in a very direct way. So it's not clear to me that you couldn't have said the monogamy paradox even without having the black hole.
Sorry, can you can you please again? The horizon played an important role here, but not where?
It's not clear to me that you absolutely need to have a horizon in order to set up a monogamy paradox.
Well, the horizon was important because the process of Hawking radiation across the horizon involved some kind of pair creation happening at the horizon. So the process of Hawking, if you have a horizon and you have Hawking radiation happening in the way Hawking envisioned it, then the idea is that every time you emit these photons in A, and then there is something else that's created in B. So you have pair creation happening in A and B. If you don't have a horizon and you just have some matter that's just being ejected from some lump of coal, then it's not the case that every time some qubit emerges, there is a partner qubit that is emitted into the system. So the idea here is, let's say you have some qubit chain.
But that's not clear to me, because if I have something that's very close to being a black hole but not a black hole, is it not envisionable to argue that some mode A that's just outside the almost horizon is maximally entangled with something close by, and therefore I run into the same paradox? Is it clear that for, say, fuzzballs that very highly resemble black holes, the paradox would be resolved in this simple way of no interior?
Well, okay, at least, you could try and ask what happens if you have a fuzzball that's being very close. So maybe, we'll discuss this a little bit more. You're right. You might end up coming to the conclusion that you actually have a firewall. So if you were to have a firewall, then so you see, where did the point that we had to have a B come from? It came not only from the fact that you had a horizon and there was some geometry outside. It came from the fact that we demanded that on this Cauchy slice, there are some correlators which are smooth in A and B. So we demanded that if you make an insertion in A and an insertion in B, that correlation function has a nice and smooth limit. So if the interior doesn't exist, then you can't make that demand. But I think you're right that if you were to look at a fuzzball that's very close to being a black hole, then somehow the correlation functions would have to look like empty space and then would suddenly have to veer away from empty space, and that might lead to a singularity at the horizon. But if you were to have a singularity at the horizon, then I think there's no reason to have a B or to have to have emissions of particles in B. If you're happy with the fact that there is the correlators and so on are singular and there's no entanglement across the horizon, then it's there's.
I guess what I'm hinting at.
Yes, please.
Sorry, what I was trying to hint at was the fact that the smoothness, these correlators. There's a local structure, as you explained, of these correlators
right.
coming from, and I could just pick any random null surface in spacetime and have this split. So there's some sort of conspiracy going on between what happens near this null surface with what happens at infinity, such that I can. So what if I made a slightly different identification of the null surface, such that I'm not talking about the interior or something defined from infinity?
Oh.
And it's not clear to me that this mode A, the very moment that I stop having an interior, will stop being entangled with something else. Or but C.
So
I mean,
of course you could,
what I want to say.
Go
So
far away. I mean, you could just make a you could just make a split
don't
somewhere
understand.
in space. Go on, please.
Go on.
You could make a split just somewhere in space-time. You could just say, I just draw a line in space-time and the modes are entangled across that. And that's fine, because then what's happening is that, that's just telling you, if you just make some split like somewhere here, right? Then of course the modes are entangled here, but that's just the entanglement of modes close by later on scribe plus as well. So, you could of course make some split somewhere, and, it would then be the case that the modes here emerge and then the modes here emerge. And there's no I don't think there's any
of course I mean close enough to the boundary, there shouldn't be any problem, any stark problem with factorization of this Kirchhoff curve spacetime, whereas at the horizon there clearly is.
Yes,
I'm asking, is it possible to see this problem before you reach the horizon? You exactly reach the horizon.
It could. Maybe can we discuss this after the firewall thing? Because the only thing I want to say is that I think let me say it another way. You see, let's say you were to define a state on the black hole which has radiation but which doesn't have the interior. I think it's possible to define a state. There are these states which are sometimes called they're called the Boole-Ware vacuum. If you look at these old papers, there were these states which were called the Boole-Ware vacuum, which were states where let's say you take like even Minkowski space. You can think of some state where there's radiation which is emerging on one side, but the space is not entangled with something on the other side. So it's possible to define these states, I think, where the interior is singular. And if you do that, if you're happy to accept a singularity sitting at the horizon, then I think it is possible to have a radiation coming out without having something sitting inside B. So if you give up the assumption of smoothness at the horizon, then I think you don't have a contradiction. But maybe we can discuss more a little bit after we discuss the firewall, and then we can talk about this again. Would that be okay?
Okay, perfect.
Okay, thanks. Yeah. Okay, great. So what I was saying was that the fuzzball gives you some clever way of sidestepping this process of the no-hair theorem. Let me also say that there is an additional aspect to the fuzzball proposal, which actually I'm not the best person perhaps to do justice to, as you can also see in my discussion with Monica. But let me just try and explain it as clearly as I can. The fuzzball proposal also says a little bit more. Here we have a diagram which suggests that space pinches off before you reach the horizon, and then the additional idea is that at here there is some fuzz, or there are some degrees of freedom that live here, and the hope is that somehow by describing how the space caps off, you will be able to count the microstates and describe the different microstates of the black hole. And there's an additional aspect to this, which is sometimes called Fuzzball Complementarity. And Fuzzball Complementarity is the statement that if you have an observer who probes the geometry at energies which are much larger than the Hawking temperature, then this observer would somehow excite. So let's say you had an observer who's falling in. Okay, so this observer who falls in, if this observer is much smaller than the black hole, then this observer would somehow excite these degrees of freedom in just the right way to see a smooth interior. Okay, so sees a smooth interior. On the other hand, if you have an observer who is at much lower energies, so if you're probing something at much lower energies, then one sees the fuzzball. Okay. And this proposal is called Fuzzball Complementarity, and this is an extremely brief and perhaps not very I'm not capturing all the nuances of the proposal. But I'll refer you to the papers on Fuzzball Complementarity for further discussion of this issue. Okay? So the idea is that you have this fuzz which lives at the place where this extra dimension caps off, and even though you have this fuzz and even though the extra dimension has capped off, the argument is that if you have an observer who's probing the black hole at high energies, this observer sees a smooth interior, and if you have an observer who probes the horizon at small energies, probes the horizon at large distance scales, then this observer sees all this fuzz that is sitting around here. Okay? So that's the idea of fuzzball complementarity. So you have a fuzzball, but you also don't have a fuzzball for some kinds of questions. Okay. Let me say one thing about the logic of these solutions. The solutions are interesting, but so there's of course one more piece of evidence for this, which is that many such solutions have been found. So there are many interesting papers which find several such solutions where you indeed can take these extra dimensions and make them cap off before the horizon is formed. So you do have regular solutions with the same charges as that of a black hole. So these solutions are always found in theories which have additional charges. They're extremal solutions, but you can find solutions with the same charges as a black hole. And so these solutions can be found, but it's important to be clear about the logic. And one important thing is that the solutions cannot directly tell you about generic states and about whether black holes exist or not, or whether there are some other states which could be black holes. In fact, the solutions cannot even tell you whether a generic state is likely to be a black hole or not. And the reason for that is actually quite simple. You see, let's say we take now the metric operator at some point. Okay, so this is the metric operator at some point somewhere in the geometry, okay, in the exterior. So I'm being schematic, I'm not being very precise, but just imagine that we look at the metric operator somewhere in the exterior. As we discussed, you have to define this operator carefully, you have to dress it to the boundary and so on. But let's say we've done all of that. Then sometime back in the first few lectures, we proved a result about this metric operator, in fact about any operator. And the result was that if you look at the expectation value in a generic state, then this expectation value is close to some universal expectation value plus some order e to the minus s by 2 corrections. Okay. Now, because this is the case, all of these different fuzzball solutions that have been found, they all differ from each other at order 1. So none of them, or at most one of them, can be this universal geometry. All of them cannot represent generic states. And in fact, it must be the case that if you were to find at some level all of these generic fuzzball solutions, then all of them would be extremely close, exponentially close to some universal solution. In fact, we can also argue just using, and in fact, the fuzzball proposal also says that if one were to use Euclidean quantum gravity, then one expects, in fact, that the typical fuzzball or this universal solution is just equal to the conventional solution. So the idea is that you have all of these solutions But if you were to look at what the generic state is, and at least outside, it must be the case that the metric basically looks almost exactly like the conventional black hole metric. So for this reason, this means that all the solutions that have been found, even though the solutions are very interesting, the solutions cannot by themselves give you evidence that you have to replace the black hole with a fuzzball. So the solutions by themselves cannot represent generic states.
Suvrat, can I try to do my Bena?
Yes, please. Yes.
Yeah, so, and maybe I think Bena student is in the audience, so he can
Okay,
correct
fine.
me.
Sure. If someone has, I'm happy to have discussion. Yeah.
So you put this e to the minus s correction to your universal solution, which might look like a black hole. I think what Bena would say, so the particular structure of the solutions, as far as I understand, is that so they're extremal black hole. They mimic extremal black holes, so they have a very, very long ADS2 throat.
Okay.
And somehow this fuzzball structure is just down the throat. So what I think they would be saying is that you just make this throat incredibly long, so long that actually the correction, and then you have some nice structure at the end of it. But if you, by just making the throat sufficiently long, you can get a lot of structure just down the throat.
Right.
So it's a little bit more subtle.
Yeah, but
it's a little bit.
Yeah, I agree with you. Actually, I don't want to go into.
And the curvature is small everywhere, so they can make this. Yeah, I think it's a bit more subtle. My personal opinion is that for such ADS2 type solutions, there might be large quantum fluctuations that wash out the classical solution, but I don't think anybody has done the computation.
Yeah, just to say once more, you.
But it's a bit more subtle.
Yeah, but you could have a long throat. So maybe there's a long throat, but you could still ask, let me go some way down the ADS2 throat and let me measure the metric at that point. So this theorem that we have applies even for the metric at that point, right? So you could go very close to the horizon, and this result still tells you that for a generic state, it would be the case. In fact, and just to say once more, to find a generic state, you would have to take a superposition of these geometries. So, if you were to take a superposition of these geometries, it might still be the case. And in fact, in some examples where we worked out, it might still be the case that, somehow it all works out because the superposition causes cancellations and gives you the e to the minus s by 2 just correctly. And then we can ask more refined questions about whether these kinds of solutions can form a basis or not. But actually, all I want to say at this point is that this, let me weaken it, by themselves are not yet, okay, we might do a lecture at this point later, but let me just at this point just weaken it so as not to get into a longer discussion. Let me say are not enough by themselves to state that black holes don't exist. Okay, so I think that this is something which hopefully everyone would agree with. Which is that if you just give me the solutions by themselves, they're not enough by themselves to state that black holes don't exist. We can discuss more about, whether the solutions are consistent and whether they can be generic states or not. I think it would be hard to make them generic states, but let's just, I think all I'm saying is that the solutions by themselves are not enough to give you evidence that black holes need to be replaced with fuzzballs. Would you agree with that?
Well, but that's not the... Right, there's supposed to be a resolution to the paradox, right?
Yeah. So I want to say, So what I wanted to say was that in fact the reason the monogamy paradox was invented. So fuzzballs have been known about for a long time, and there's been work on the fuzzballs for a long time. The reason the monogamy paradox was invented was to say that even though we may not have solutions corresponding to generic non-extremal black holes, we have this indirect argument that even for black holes which are non-extremal and big Schwarzschild black holes, they must have structure at the horizon. So let me try and say how I think of the logic of the fuzzball proposal at least. So this is my structure. This is the Hilbert space. In this Hilbert space, we found some solutions, which I think it's fair enough that the solutions that have been found don't cover the Hilbert space. So these are some solutions. One can discuss how much of the Hilbert space they cover. But for the rest of the Hilbert space, we give an indirect argument using the monogamy paradox that the rest of the Hilbert space is also covered by fuzzballs. In fact, that's all I wanted to say. I just wanted to say that the solutions by themselves are not used to advocate for the fuzzballs everywhere. At least this is my understanding. But rather that the solutions are used to say, look, at some points in the Hilbert space, we have some things which are not black holes. And in the rest of the Hilbert space, you have an indirect argument using the monogamy paradox, which tells us that you have fuzzballs and not black holes. Is that clear? And I hope it's fair. If it's not fair, please correct me. Once again, I know there might be people in the audience who know much more about fuzzballs. So if I'm inaccurately representing something, I'd be very glad if you were to correct me and accurately state this. So just to say, the only point of all of this was to say that we have solutions. The solutions give us some evidence, but the solutions are covering a small part of the Hilbert space. And the reason for the monogamy paradox was, to say that, even though we don't have all solutions, and it might be very hard to find all solutions, look, here's this other argument, which comes from the information paradox, which tells us that you must have structured the horizon. So I just wanted to clarify the structure of the logic. The structure of the logic is not that the solutions tell us we have structured the horizon, but that the solutions give us some evidence, and then for the rest of the Hilbert space, we have this other argument that tells us that this is the case.
Sorry, Suvrat, so am I supposed to conclude then every point at the Hilbert space must be some sort of superposition of fuzzballs in order to be able to apply this to get out of the monogamy paradox?
I think so. I think that's if you want to get out of the monogamy paradox, you would have to argue that that generic states are superpositions of fuzzballs. If you wanted the fuzzball,
that's what I thought they said, but I'm not an expert either.
This is my understanding of what they said as well, of what the argument was. I think this understanding is accurate. That one would like the generic states are fuzzballs. If generic states are black holes, then one would just be back to the black hole, to the usual paradox. Then the fact that you see, we all agree that the fuzzball solutions exist. But if the fuzzball solutions are taking up some corner of the Hilbert space and they're not generic states and they're not directly relevant for resolving the paradox, we would still have the paradox with black holes. And at least if you look at the paper of Mathur that I referred to and many other papers, the idea is that, it is the fact that generic states are represented by fuzzballs which resolves the paradox. Okay. Once again, if there are questions, you can say them now, or please feel free to speak up and say this. I'm actually, as you see, this is not something which I work on myself, and but I think I just wanted to fairly represent what the fuzzball resolution is. Let me move on to a slightly different resolution, which was the other resolution, which is the resolution using firewalls. So firewalls are actually simpler to understand than fuzzballs. Let me also say a little bit about the logic of firewalls. So firewalls, there was actually a fair amount of literature about firewalls 10 years ago. And there was initially an AMPS paper that popularized the term firewalls. The AMPS paradox is the monogamy paradox, okay? Is the same paradox. So in fact, I think it's a little unfortunate that initially, it was not recognized that the paradox that was advocated in the AMPS was the same paradox that had been advocated a few years earlier in the discussions in the fuzzball. It is now clear, and in fact, if one looks at the later versions of the AMPS paper, one looks at it now, they make it very clear that the paradox they're referring to is the same paradox as the paradox that was set out by Mathur a few years earlier. And so, this is not really, there's no really a separate AMPS paradox. There is a single monogamy paradox, which was developed earlier. And this is where the term firewalls came from. I want to distinguish this from the AMPSS paradoxes, where S is Douglas Stanford, who was added on, who participated in some of the later papers, and also some other papers by Marolf and Pulczynski. And the reason I want to differentiate this is that these paradoxes, they applied to large ADS black holes. So there is a separate set of paradoxes that we will discuss later in the course that apply to large ADS black holes. But the paradox, the initial terminology of firewalls came from the AMPS paradox, and it's the same monogamy paradox. is the case. So there are separate and very interesting paradoxes that one can ask for large black holes. And when I say large black holes, I mean these are black holes which don't evaporate. And so they are statistically slightly different from small black holes. So we'll come to them. But right now, I just want to discuss the original monogamy paradox and the firewall resolution to the monogamy paradox. So even though the paradox that AMPS set out was the same as the paradox that Mathur set out, the resolution that they put forward was slightly different. And the resolution that they put forward was the following. AMPS stated that let's compute, let's assume that we agree that we have this problem with the monogamy of entanglement. And AMPS also said that we don't have an interior, but they said the following. They said that we will accept the fact that the geometry outside, so AMPS will accept that the geometry outside or all the way to the horizon resembles the conventional geometry. This then doesn't allow us to make any criticisms that we have about, various operators being close to a universal geometry, or, can you use the metric to capture these e to the minus s by 2 corrections, or can you have variations and so on. So AMPS say, fine, we'll just accept that the geometry all the way to the horizon represents the conventional geometry. But nevertheless, when you reach the horizon, there is no interior. Okay. Now, if you accept these two statements, that there is no interior and the geometry all the way to the horizon resembles the conventional geometry, then as we were discussing some time back, you will immediately find that that actually leads to a singularity at the horizon. The reason it leads to a singularity is the following. Let's say we try and compute the expectation value of the stress energy tensor at the horizon, okay? At the horizon or just near the horizon. Okay? Then remember, how do we compute the expectation value of the stress energy tensor? One of the things, if you have some scalar field that's propagating in the space-time, you would need to compute this expectation value is you would need to compute the expectation value of a 2-point function of the scalar field at points x1 and x2. And then you would need to subtract off some counter terms. Where do these counter terms come from? These counter terms, if you just open Birrell and Davies, the leading counter term, in fact, comes from the fact that you assume that this 2-point function looks the same as the 2-point function that we had earlier, right? There was this normalization factor, and then we had this term that came from here. This assumption goes into these counter terms, and that's how you regulate the stress tensor. If it is the case that phi x1 and phi x2 does not have this short distance behavior, then you see that the expectation of T mu nu is bound to diverge. So if it is the case that at the horizon, so this is the horizon, if you have the conventional geometry outside and you have nothing inside, so there's no interior, or, then you would, at least, just behind the horizon, you don't have the right entangled modes, then you see that you would not have this 2-point function. If you did not have this right 2-point function, then you would find that T mu nu diverges at the horizon. Okay. And so the firewall is kind of saying that, we agree with the fact that you cannot have partner modes that are entangled with the modes outside. But the place where the firewall diverges from the fuzzball is that A, it doesn't say there's any notion of fuzzball complementarity. It says that if you have an observer who falls in, the observer will just hit a ball of fire. And the reason the observer will hit a ball of fire or will hit some energetic particles is because, there are no particles behind the horizon to be correctly entangled with the particles in front of the horizon. And if that happens, if you break the entanglement at some point, then you can compute the expectation value of the stress tensor, and you find the expectation value of the stress tensor diverges. So the picture that one has for the firewall is some picture of this kind. So you have some horizon, and then behind the horizon you have some firewall. Okay, so this is R equal to RH. This is R equal to RH. and this is a firewall just behind the horizon. And it's a very similar resolution in spirit. It once again drops the idea that SAB is smaller than SA or SAB is smaller than SP. Okay. It drops this idea. Just to remind you what SA and SB were. See if I can still paste. I can't paste anymore. I can't paste it. Anyway, just to remind you what A and B were, let's just go back to this figure. Okay. So, because you don't have a B or you don't have a correctly entangled B, it tells you that, because you've replaced this with a firewall, it tells you you don't have to have SAB smaller than SP. And therefore, you see that you have a firewall. Now, it could be actually that after the firewall, normal space resumes, right? If you break the entanglement at the horizon, it could be that after that, normal space resumes. But, we don't know what that is. And that's actually, as far as I know, not been made very precise within the proposal. The basic point is that you need to break the entanglement at the horizon, and breaking the entanglement at the horizon leads to a firewall. Okay. In some sense, I think that this is a more reasonable proposal than the Fuzzball proposal, because it says something pretty straightforward. It doesn't try and say that, at least, so this is what I believe. But I think that if one wanted to break the entanglement, or if one wanted to say there's no interior, I think one would have to work much harder to try and make the Fuzzball story consistent than make the firewall story consistent. But the firewall is a story which just says that you break the entanglement. When you break the entanglement, you don't have an interior, and you have a singularity, and then they're not obliged to explain to you anything more about the singularity. Okay, so that is the story of the firewall. Is there a question?
Yeah, should you not give some mechanism for this breaking of entanglement? Or?
Yeah, thank you. So I will. That's in fact one of the weaknesses. That's exactly the question. So, what are the weaknesses? There's no good mechanism for producing the firewall, for producing it, for producing or for stabilizing it. So, not only is there a problem with the fact that the firewall forms at some point. If you really have a picture of this kind where the firewall forms at the horizon and then ordinary space resumes and the interior is the usual interior, then the firewall would tend to fall in. There's nothing which can stabilize something behind the horizon, because the no-head theorem actually applies outside and inside the horizon. So if you have some classical ball of fire which is sitting, or classical high energy excitations which are sitting close to the horizon, they would tend to fall in. So there's no good mechanism for understanding this. And there's clearly the other problem is it's a large violation of effective field theory, because it tells you that quantum effects extend all the way out to the horizon. Okay. So we have a problem. These are the weaknesses, but there are also some strengths in that it resolves the monogamy paradox, and it doesn't have to explain any additional things. So in fact, I realized I promised to fill up a table at the beginning. Let me try and fill up the table of the various proposals, and then we'll come to a third one. Here it is. So we had fuzzballs. The evidence is solutions, but the solutions are not generic for the fuzzball. And then we have the monogamy paradox. So the criticism is that you need to find the criticism is that you need to make it consistent with statistical mechanics, with statistical constraints, and this also in some sense is a large violation of effective field theory, because this is also telling us that you have collapse, and somehow the collapse stops in some cases. So this also gives us a large violation of at least naive intuition. Okay, so we need some, there are mechanisms that people have developed that try and explain how, if you have collapse, the collapse stops and you tunnel into a fuzzball and so on. But it's clearly something that one needs to answer. With firewalls,
Suvrat,
yeah.
Isn't your monogamy paradox already a large violation of EFT intuition?
Right now, it's just a paradox. I mean, we don't know. So I'm just describing resolution.
Yeah, I understand, but it seems, I mean, it is some violation of, you know, what you thought about the structure of, you know, effective theories in curved spacetime. So
yeah. So maybe it's okay. I mean, I'm just saying this is something one needs to explain why it is that this works. You know, so the monogamy paradox. This is a resolution. I mean, we'll discuss some other resolutions, and you know, you might say that this is a paradox, and I'm just pointing out that. If it was the case, you would need in the end some explanation for why it is the case that quantum effects extend all the way out to the horizon.
But that is that necessarily a bad thing?
Maybe it's not. Maybe it's okay. I'm not saying the criticism is a fatal criticism. I'm just writing down right now some criticism. It could be that
well, I'm debating whether it's a valid criticism. Yeah, okay, it's a feature. For sure.
It is a fact that, you know, there's a large violation of naive EFT intuition. So now whether that's you know, whether that's necessary or not, we can discuss, and whether the monogamy paradox is sufficient for it, we can discuss. But okay, let me just say something about firewalls. So the evidence for this actually doesn't come from any solutions. So there's a monogamy paradox, and then there's some indirect evidence that can come from AMPSS paradoxes for large black holes. You know, you might believe that if large black holes have firewalls, maybe evaporating black holes too, but we're not going to discuss that. Okay. So there's some indirect evidence that may come from that, and I think that here also we have a problem in that we have a large violation of naive EFT intuition. Okay, it's telling us that, you know, the monogamy paradox is telling us that we need to radically change what we think of the classical solution. Okay, so there's a third. I mean, there is even here a naive violation of EFT intuition. Okay, good. So now in the last 10 or 15 minutes, I want you to describe a third resolution, which we'll spend some lectures covering. This resolution is what we will call the holography of information, and I'm going to describe what that resolution is very briefly, and then we'll discuss it in more detail later. And I'll also tell you what I won't tell you so much what the evidence for this is, but I'll explain what the criticism is at least, and then we can discuss what the evidence for it is in the next lectures. Okay. So let me explain what holography of information means. So holography of information, there were many other resolutions that were proposed, and they all mean the same thing. There were these resolutions that were called A equal to RB, complementarity, ER equals EPR, and we are going to subsume these resolutions into what we'll call the holography of information. But let me just explain what the spirit of these resolutions is in the last 10 minutes of the lecture. So the spirit of these resolutions.
Sorry, there's actually one question. You want to take it now, or?
What's the question? Where's the question?
Yeah. The question is the T mu nu a delta function on the horizon? That's why it diverges, or?
Yeah, so T mu nu would have delta. I mean, it depends exactly on how you break the entanglement. If there is an interior and you've broken the entanglement exactly at the horizon, then you would get a delta function at the horizon. That's not why it diverges. You know, the point is that T mu nu will have diverges because you've broken the smooth structure of entanglement, and that's why T mu nu diverges. You know, whether it has a delta function support or not depends on what you say for what happens behind the horizon. But certainly T mu nu goes to infinity at the horizon, and then, you know, whether it stays at infinity, it's an infinite wall, or whether it comes back down to zero is something which you have to specify for what's happening in the interior. Okay. So let me explain now what the set of these resolutions is. A equal to RB, complementarity, and ER equals EPR. So let me remind you that the way we came up with this was initially, let me go back to the derivation we had yesterday. We had this monogamy inequality, which was CAB squared plus CAC squared is smaller than 8. But this only makes sense if A, B, and C are different subsystems, right? There's a more precise way of saying that, and that is that this only makes sense if all of these operators, in particular, you know, A commutes with B and A commutes with C. So it is important in this case, in particular, one of the relations we need is that this inequality only makes sense if all the operators bi commute with all the operators ci. Okay? Why is that the case? It's quite simple to see that. Let's say we just set C1 equal to B1 and C2 equal to B2 in the CSH. Okay, so let's say we just say C is the same system as B. If we do that, then of course it's clear that we can clearly get CAB squared plus CAC squared equal to 16, right? We can get CAB squared plus CAC squared equal to 16 because, we've just identified B and C, and therefore, we can make CAB squared as large as 8, so we can make CAB squared plus CAC squared as large as 16. But even here, remember that for this to happen, it must be the case, right, even for CAB squared to be larger than 4, we must have the fact, it must be the case that B1, B2 is not equal to 0. We discussed this when we discussed these results on quantum information, that the only way that CAB square could be larger than 4 is if B1 failed to commute with B2. And since we have identified B and C, it must be the case that B1, C2 is not equal to 0. So even here, we see that whatever you do, if you want to violate, even in the situation where you identify B and C, you will see the fact that you've identified them from the fact that the commutator of B with C is not 0. Okay? So it's very important that this entire inequality requires this, and if you violate the inequality, you should first check to see if BICJ is 0 or not. Okay? Now, let me remind you that in this proposal, when we derived these inequalities, there were two parts to this derivation. Right? Two parts to the derivation was, first we looked at these operators on opposite sides, which were B and A, and then we had C somewhere far away here. And in A and B, we wrote down explicitly within effective field theory some operators that gave us CAB squared larger than 4. Now, within effective field theory, when you turn on gravitational effects, one can also commute what do you expect for the commutators of these operators. If you write down the operators precisely, you might be able to compute them. But let me try and give you an estimate for what you would expect. You would expect that the commutators of A and B are of the order, when you turn on gravitational effects, just by dimensional analysis, of the order of G Newton times e to the d minus 1, no brackets. Okay? And that is roughly 1 over s. Okay? So you expect that these quasi-local operators A and B that you defined, these field operators which you were smearing to get this get this violation of the Bell inequalities, had some commutator which was of the order of 1 over s. But on the other hand, let me remind you that we never wrote down the operators in C explicitly. Were not written explicitly. Okay? We just argued that these operators must exist, and they must exist. Why? Because we have some general result from quantum information that tells us that if you have a generic state and you have some operators in A, then those operators in A must in some way be entangled with some other operators, and those other operators must live in C. Okay? But if you do that, then you see that you find that you have not said anything about the complexity of those operators. So it could be that C is a very complicated operator. Okay? There is C operators, and in fact, if you look at models from just these bit models that we were discussing, and you try and ask, if you have this kind of entanglement, how complicated do these operators have to be, these partners that are forced to exist by some genericity arguments. So it could be that these C operators are very complicated. Right? And by very complicated, I mean that maybe they have like of the order of S insertions of the fields. Okay? If these operators are of this form, then this argument we had that, we know that the field operators, these quasi-local field operators have small commutators, does not apply anymore if you have such large insertions. And so these proposals, which are A equal to RB or ER equals EPR, etc., all of these proposals suggest that it is indeed the case that the commutator is large, and they suggest that this BICJ commutator is large. And large meaning all of these operators are bounded operators. So it suggests that the commutator is order 1. Large just means not close to 0, being close to order 1. And therefore, one way to state these proposals in words is that the degrees of freedom in the interior are identified. You know, if you have a large commutator between 2 degrees of freedom, it's telling you that these operators Bi and Cj are probing the same part of the Hilbert space. They are not probing different parts of the Hilbert space. So the way to say this in words is that the degrees of freedom in the interior are identified, or are scrambled versions of DOF of the degrees of freedom far away. So this is the essence of these proposals. It is to say that, you know, we were not, you know, we assumed that the Hilbert space approximately factorizes, and that led us to this assumption that these commutators are all approximately 0. But we know that in gravity, the Hilbert space doesn't factorize exactly. In fact, we spent a lecture when we were discussing Hawking's paradox, describing how the Hilbert space doesn't factorize. Even then, it is true that, you know, for simple operators, the commutators are small. But it's not necessarily true that for very complicated operators, the commutators are small. And these proposals suggest that the resolution is that you don't have a monogamy paradox, because in fact, you should identify these operators B and C. Okay? Let me also just explain why the phrase ER equals EPR is sometimes used to describe this. There is a well-known, a very well-studied example within the ADS-CFT literature, which we will also discuss, which is an example of what's called the eternal black hole. And in the eternal black hole, we have the fact we have a CFT1 and a CFT2, and these two CFTs are entangled with each other. And because they're entangled with each other, we say that the dual in the bulk is an eternal black hole, which looks like the Penrose diagram that we've drawn on top. But if you look at this Penrose diagram, you will see that the eternal black hole has the property that it has 2 horizons which open out to different asymptotic regions, to 2 asymptotic regions, but there's a single interior, but only one interior. So this was a point that was made by Wheeler, and if you look at Misner, Thorne, and Wheeler, you will find in that book a description and a diagram of these wormholes. Another way to think of the Penrose diagram that we have drawn is to think of both of these black holes as actually living in the same universe. So not in 2 different universes which are connected, but rather in the same universe. And the way this diagram is sometimes drawn is that you have a single universe. This is just one spatial slice. And on this spatial slice, you have a black hole which connects. So this is BH1, this is or horizon 1. Which is connected to horizon 2. But if you fall in from here, if you have an observer who falls in from here, and you have an observer who falls in from here, they think that they're falling into black holes in very far away parts of the universe. So maybe one of the horizons is near the Earth, and maybe the other horizon is somewhere in the Andromeda galaxy. And one observer falls in from this side, the other observer falls in from the other side. In fact, it's not possible to use this black hole, at least in the simplest case, to actually traverse. You can't actually cross from one horizon to the other, but these 2 observers can go inside and can meet here. Okay? So you can write down these solutions of this kind where you have these 2 systems, these 2 black holes which are very far away but share a common interior. But if you think of the dual that I have drawn on top, this dual describes one theory which is entangled with another theory. So the idea of the ER equals EPR proposal was that if you take the black hole, and once again, if you take the black hole, once the black hole, once a lot of the radiation has streamed out here, then the black hole that remains is kind of maximally entangled with the radiation in C. And so this setup looks like the eternal black hole that you had previously. In fact, you could take the radiation in C and maybe you could collapse it into a black hole. And therefore, in this setup, you had two CFTs which were entangled with each other, but the interior of the black hole that you fell into from the left CFT was described by degrees of freedom that were living in the right CFT. Okay? So even if you fell into a black hole that looked like it was living in the left CFT, the degrees of freedom there would be described by some other system which was living very far away. And the idea was that if you think back here, once a lot of the black hole has evaporated, and once the black hole is maximally entangled with the radiation in C, maybe the interior of the black hole is described by the degrees of freedom that act on the radiation. Okay? So that is the spirit of the ER equals EPR proposal. I should say a note of caution. I think that many times ER equals EPR is taken literally. At least I think that ER equals EPR should not be taken literally. It's not the case that every time you have a qubit or an EPR pair that you have wormholes that connect them. But rather, I think that ER equals EPR should be interpreted as the following statement. It should be interpreted as a statement that the duality between the thermophile double and the eternal black hole, that this lends support to the A equal to RB resolution. Okay? It lends support to the fact that, A equal to RB is just some term. It lends support to the fact that sometimes it might happen that you might have degrees of freedom far away, and those degrees of freedom are describing, some degrees of freedom here are also described, have a dual description in terms of degrees of freedom that are very far away. Okay. So this is the spirit of the proposal. Let me now say a few things. There are obvious criticisms of this proposal, and the obvious criticism of the proposal, if you look at the original papers on the subject, but the criticisms of this proposal are we violating what Mathur in his original paper calls solar system physics? Okay? In that, and what that means is that, if you take a black hole, which is very big, say a black hole even of the size of the sun, or a black hole which is like the supermassive black hole in the galaxy, and you allow it to evaporate, the radiation goes out to a very, very, very large distance. I mean, it's really astronomical distance. There was a question in the assignment asking you to compute how far out the radiation goes to. So for a big black hole, right, the early radiation is very far away. So we are somehow saying that this radiation very far away describes, some degrees of freedom in the interior. So how can it describe the interior, right? It's not like some small effect which is happening on the Planck scale. We are saying that, we have these degrees of freedom that are very far away, and these degrees of freedom are somehow, very far away degrees of freedom are describing the interior of a black hole. That might be here. Maybe there's a black hole in the Earth, and there's some early radiation which has gone off very far away. And somehow there's a manipulation you can do in the early radiation that can affect the interior of the black hole that lives here. And that seems something strange. And are we violating solar system physics? And the second question is, what is the origin of such effects? Okay. So what is the origin of such effects? Are we postulating new physics? Are we just coming up with a postulate because we like the fact that, we like the usual black hole solution? Maybe we just came up with some ad hoc postulate saying, oh, we can save the usual black hole solution because we don't like fuzzballs and we don't like firewalls. So maybe we can just save the black hole solution by making some postulate of this kind. Okay. This is the criticism of this proposal. Let me just fill this in. I'll just take a couple of minutes more and then I'll be done. Let me just fill in this table. So there's a whole lot, and the evidence for this comes from, in fact, the evidence for this we'll discuss in the next lectures. I haven't so far given any evidence for why this is the case, although I have explained the criticism. It seems to violate solar system physics. Okay. In that it seems to involve some large violation of locality over long distances. So this is the summary of the three things that we said today. Let me just say what we will try and develop in the next lecture. What we will try and develop in the next lecture, in fact, is that this principle that we are describing of degrees of freedom in one place being described by degrees of freedom far away can be, in fact, reformulated in some nice way And the nice way that we will use to reformulate the principle, let me just write that down and then I'll stop the lecture, is the following. We are going to formulate the following principle, which is what the name I used, but I didn't explain. And the principle is going to be that in any theory of quantum gravity, okay, a copy of all the information on a Cauchy slice is also available near its boundary. And so this is an interesting kind of statement. And the statement can be understood in this way, that if you take some region and you have some region, let's call this region R, and outside is R complement, then the statement is that you might have thought in a quantum field theory, this R might be a black hole or something else here, that you have some degrees of freedom that live here. But in fact, there is another description of these degrees of freedom, maybe in terms of some very complicated combination of degrees of freedom that live far away. Pink dots. Okay. So there's another description of these degrees of freedom in terms of complicated combination of degrees of freedom that live far away, so that somehow the degrees of freedom far away, there's some complicated combination of degrees of freedom far away that describe these degrees of freedom that live inside R. Okay. So the statement is that the information in R is also available in R tilde. Okay. And the important point, this of course, is that first of all, this does not violate solar system physics, in that we will have to ensure that first of all, it does not violate solar system physics, in the sense that it's not the case that locality is violated for simple experiments, or for experiments we would do in the solar system here. So I'll have to explain how that is the case. So we'll have to address these criticisms. It does not violate solar system physics. And the second point, which is perhaps the most important point, which is a point that I think cannot be emphasized enough, is that it does not even involve new physical postulates. Okay? This is not going to be some ad hoc postulate that we're going to make up because we like this octopus picture, but it's going to come from a conservative analysis just of trying to understand how quantum mechanics and gravity fit together. So it does not involve new postulates. I mean, we will of course have to make some assumptions, but we are not at any point going to ad hoc introduce some new non-local terms in the physics. So we are going to have to analyze carefully the structure of how quantum mechanics and gravity fit together, but we are not going to introduce like new ad hoc postulates. So far these are just claims, but these are just claims in that I would like to say that we will, in that there is a response to the criticisms of these proposals. There are obvious criticisms of this proposal, but we will spend some lectures trying to develop some evidence for this proposal. Okay, so that's actually all I wanted to say. Let me just conclude by reminding you of this summary slide that we had here. Oops. Oh, I think I destroyed the summary slide. Okay, anyway, I think I destroyed the summary slide in my attempt to copy it. So we just have the criticisms of all the proposals that are left. My idea was to create a slide with a summary. So let me just say it in words. So I described 3 proposals that resolve the monogamy paradox. I described the fuzzball proposal and the firewall proposal. Both of these proposals say that the interior ceases to exist. The fuzzball proposal, says that there's nevertheless, for some experiments, for an infalling observer, a gentle experience. The firewall proposal says that, you really have a singularity at the horizon. And then there is an additional proposal, which we discussed at the end, which I haven't given you any evidence for. And the additional proposal is that, it could be that perhaps for a black hole, this violation, the fact that the Hilbert space factorizes is not true. And in fact, these commutators are large commutators. And that was the proposal that we wrote here. Maybe it could be that the degrees of freedom in the black hole interior scrambled versions of degrees of freedom far away. And if that was the case, then indeed, the monogamy paradox would again be resolved. But one has to explain where this effect arises from, which we'll do in the next few lectures. So I'm sorry for going a little bit over time, but I'll stop here and we can have more questions if there are some.
Okay, Suvrat, can I ask a small technical question about the
Yeah, sure.
fuzzballs? So you mentioned this metric operator that you're using to see the departure from like its typical value. I mean, if you take one of these geometries that have very, very long throats, I mean, instead of measuring the metric down the throat, I could just measure many correlators, say the asymptotic ADS, many correlators at the ADS boundary. It should be equivalent in principle.
Sorry, maybe there's some problem with the audio. I was not able to hear very clearly, but if I thought you asked this metric operator, is it just measuring the geometry? Is it just measuring the metric down the throat? Yes, it's just measuring the metric down the throat.
Yeah. So let me make the in principle equivalent measurement of many detailed correlators near the ADS boundary of this black hole. It should be equivalent.
Yes, you can make a detailed measurement of many correlators. Yes.
Yeah. So then what happens that for these very long throated geometries, those correlators would be very, very, very close to the black hole value because the throat can be made arbitrarily long. So this, if there's not other problem with the geometries, this can be made to look arbitrarily close to a black hole geometry.
So the claim is that somehow, so you have to make the geometry like long, and the length has to be controlled actually by some ratio of ADS scale to Planck scale. So you have to make it parametrically long.
Exactly, you have to make it parametrically long. So if classical reasoning works, then it seems that you can just put the information about the structure of the state, the fuzz, you can just put it down the throat. But at the price of making this throat incredibly long, and then your sort of simple operators that have to take the typical values, actually they seem to be taking the typical values.
Yeah, the result is actually not,
I think.
Yeah, go on, please. Yeah.
So all I'm trying to say is that in that case, in order to make an argument against this, one has to do something a bit more subtle because there might be problems with the length of the throat becoming.
Yeah, just to say, I mean, maybe you misunderstood the point. I was not trying to today say that the fuzzball proposal is not viable. I was not trying to make that. I mean, it's an argument. I mean, as you know, I believe in, but I was not today at least trying to say that I mean, nothing I said in this lecture said that the fuzzball proposal is not viable. I was just saying that you have to deal with these questions of, you know, how you address this. I mean,
you did say that you liked it less than the firewall.
Well, oh yeah, so I like it less. That's a question of personal.
I might disagree with your ordering.
Well, fine. I mean, okay, that's a, yeah. I mean, I said that it seems less issues you have to deal with if you talk about the firewall. But I certainly, there's nothing I said today which said that
Fine. I think my comment referred more generally to some discussion we could have about fuzzballs than your particular.
Yeah, so I, in the case that you're mentioning, I think the issue would be indeed of how you stabilize this throat against quantum effects. One could of course say that one goes very, very close to the horizon. So if you reparameterize everything, or if you think of a non-extremal black hole, then you could say let me go like Planck length from the horizon. I mean, the analog of this for a non-extremal black hole would be where you don't have these long ADS2 throats. Let me go like Planck distance away from the black hole, and then and then you could say that, but then you would say what is the value of looking at the classical solution. So the classical solution stops being trustworthy well before that because quantum fluctuations are the same size as the classical.
Yeah, I'm just saying that for the extremal fuzzballs they construct, which are the only ones that I think they construct.
Yeah, but even
the intuition is a bit more subtle, and the quantum effects will probably take place over large scales.
Even there, actually, even for the two charge, the Lunin-Mathral geometries originally, I mean, with Pushkal, who I think was on this call sometime earlier, we computed, you can quantize those geometries. So you can compute the size of quantum effects. And those quantum effects are already competing, are already becoming significant if you try and do this. So, at the scale at which the typical geometry deviates away from the conventional geometry, at the same scale, the quantum effects become important. So if you're solving the classical solutions to find the quantum effects, then if you're solving the classical equations of motion to find the solutions, then those solutions stop being reliable. And this is something one can check in the two charge geometries already, I think, explicitly.
Right.
So if one tries to
I think we completely agree, but
yeah, but I think you're right. You could try and make it consistent with statistical mechanics by playing some game of this kind, but then you would have to deal with other problems. So yeah.
Yeah. All I wanted to say is that it's not super obvious that the proposal doesn't work, because one has to deal with all these subtle issues having to do with
I agree. You have done. I agree, and we acknowledge you have done your duty to your colleagues. So yes, I agree.
Great.
Yeah, we acknowledge on record. But nothing I was saying today suggested that the proposal is unviable. Just to be very clear, if I was not, I didn't say that the proposal is unviable today. I was just saying, look, here's a proposal. Here is some of its criticisms, and here are some of the advantages. And I said, in fact, for the last proposal also, that here are some criticisms. So it's which we'll follow in the next things. I see there's a question about is there resolution? Where's the reference to last resolution monogamy paradox? What is A and RB in A equal to RB? Thank you for the question.
So Suvrat, he actually has a raised hand. Maybe he can just unmute himself.
Rifat has a raised hand?
Yeah,
sure.
Rifat has a raised hand, yeah.
Hi. So you had this B1 equals to C1 in some place, right? And B1, you take this field and you smear it with some smearing function which has some compact support in the region B. And using those such operators, you construct B1 and B2. And similarly, if you smear it with a smearing function with the compact support only on C, then you construct C1 and C2. Then how do you know that you can write C1 equals to B1? Because their compact support regions are entirely different.
Yeah, exactly. So, it would have to be the case somehow that these quantum fields that you thought were separate are somehow not separate. So, these C1 operators were not written by taking a field and by smearing it with something. There were some complicated operators that could have been composite operators out of many, many insertions of fields. So somehow we will have to argue that if you take a complicated polynomial, like maybe an order S polynomial of some fields far away, you need to identify that operator with some operator which looks like it has compact support somewhere else. And the reason this is reasonable, the reason this is plausible at all, is because the Hilbert space doesn't factorize. And as we emphasized a few lectures earlier, this operator that you're writing in the middle or in the interior, which you thought had compact support, doesn't actually have compact support because it always has to be dressed in some way. So there is really no notion of a local operator in gravity. You only have a notion of a quasi-local operator, some operator that behaves like a local operator for simple correlators. But if you start asking about very complicated operators like the operators in C1 and C2, then this notion of quasi-locality would not work. So this proposal was explored in the early days of the firewall proposal. For example, there's this paper we wrote with Kyriakos, which is called an infalling observer in ADS-CFT, where we discussed this proposal in some length. In fact, in this review that we are using as lecture notes for this proposal is again discussed. And when we discuss the holography of information, we'll discuss this proposal some more. So there's a lot of since you asked for references, this is one place where you could find more references and more details. But we'll discuss it ourselves later. The other question, I guess, was what was A and what was RB? A is equal to RB is actually just a term in that, one region is a scrambled version of another region. So in the old days, one of the regions was being called A and the other was being called B. And one was saying A is a scrambled version of B. For us, actually, we should more say B is equal to RC, in that the region inside is a scrambled version of the region far away in C.
Okay.
So A equal to RB is just, it's a bad name for just saying the degrees of freedom in one region are scrambled versions of degrees of freedom elsewhere. So go on, please.
Okay, and just to be clear, so we are violating the axioms of algebraic quantum field theory, is it? Because
but the axioms of algebraic, so first of all, you see, you have to be careful for even writing down these operators in gravity. The moment you even write down these operators in gravity, you will find that the operators have to be dressed. So the operators are not actually localized even to start with. So it's not like there are axioms you could write down for there's no notion of local operator algebras unless you're talking about special regions like maybe an entanglement wedge in ADS-CFT or some region in the asymptotic boundary. So it's not like there's some axiom that we are violating that holds in the theory of gravity. The moment you write down local operators, you see from the get-go that these operators are not local and they have to be dressed to the asymptotic boundary. So the fact that the commutators are non-zero is just, it's just something you can't avoid. Now, the question is whether the commutators are large or not, and that's a discussion which we will have. But the fact that the commutators are non-zero is just something you can't get away with. It's just built into the fact that the operators have to have Wilson lines that go all the way to the boundary.
So is it like if I take a very big black hole, then wouldn't I expect the the theory to be very close to the actual QFT encoded spacetime that I have, and then in that case, the commutators will go arbitrarily close to 0. So
Yeah.
can I say
So
that?
that's a very appealing. Yeah, go on, please. Yeah.
Yeah. So that's it. I was
Yeah,
just
thank
asking,
you.
can I say
That's
that?
a very appealing assumption, which is made again and again, and it again and again leads us into paradoxes. So
Okay.
thank you. You stated very clearly, actually. Let's say we take a very big black hole and we go far away, and then it must be the case. How can it be that these commutators are important? See, the issue is that there is something else you're scaling up at the same time. If you take a very big black hole, you also scale up at the same time the complexity of the operators that you're measuring far away. So if you're measuring more and more complex operators, because you have to measure operators with up to C insertions when you're far away, with up to S insertions when you're far away, where S is the entropy of the black hole. So you're right that, in some sense, you're doing something to try and suppress the commutators, but you're also doing something to scale up the operators that you're looking at. And those two effects balance each other out. So in the end, you find that, you're not able to, for some questions, in particular for the questions that are relevant for fine-grained quantum information questions, you cannot assume that the Hilbert space factorizes, and these effects are important. For some other questions, if you computed a 2-point correlator of quasi-local fields, and if I told you this effect was important, that would clearly be wrong. But for some other questions, such as correlators involving these very complicated operators, you can't rule out the fact that these effects are important, because while you make the black hole large, but there's something else you make large as well, which is the complexity of the operators you're measuring. And that's why, next we will now go on and prove that these effects are important. But it's not. This is the reason why you would believe that they should be important in the first place.
Okay, thank you.